Okay, so here we are with classwork 13, where we're going to talk about sampling distributions. So to start with, we're going to use an example that I've used in past classes where I show this picture of these two gentlemen and I ask the class to vote. They vote secretly on a piece of paper. Um, how much? I ask three questions. I ask on a scale of 1 to 6, with 1 being that guy's definitely not Tim. There's no way his name is Tim. To 6 being I know that guy and his name is definitely Tim. I ask, okay, well, rate from 1 to 6, how much does this guy on the left look like a Tim? All right, so you may want to think about that for a second. Do you think he looks like a Tim? How much? 1, 2, 3, 4, 5, or 6. How would you rate him? From 1, not Tim, to 6, definitely Tim. And same thing for this gentleman on the right-hand side. How much does he look like his name is Tim? Then the third question, so we have a 1 through 6 for this one, a 1 through 6 for this one. Again, it's totally up to you. People have different answers. And then I ask, okay, between the two of them, if I told you one of them is named Tim, who would you think is named Tim? The guy on the left or the guy on the right? So you may want to just decide for yourself before we continue. Who do you think is Tim? The guy with the curly hair, the guy with not so much hair. So I've found that it's easier in our online environment to use a past semester's data instead of trying to update it every single semester with the new numbers. It's easier when we're in class together. We can all just count it and write it down. But for online, it's harder because obviously we can't all be together and vote. So we're just going to use some data that I used from a previous semester, but this is some real data that was actually generated from my statistics classes at Valley College, probably about a year ago, maybe a little over a year ago with the pandemic. So I pooled the data from my two statistics classes together, and we counted how many people picked the guy on the left as Tim, how many people picked the guy on the right. So the guy on the left, 27 people chose him. The guy on the right, 18 people chose him. Now, if we add those two together, we can see, you can probably do this in your head, but just so we are all on the same page, that adds up to 45. There were 45 total votes between my two classes. 45 people happened to be there on whatever day we collected this data. Now, the next question, you may want to pause and see if you can answer this yourself before we move on. But what was the proportion that picked the left guy, the curly-haired guy? Right? So how do we figure out a proportion is the question. So the proportion would be the number of people who chose him out of the total number of people. So if we do that, let's move this over. 27 people chose the guy on the left, and I'm going to divide by the total number of people who voted, which is 45, and that's going to give us the proportion that picked the guy on the left. So 0.6. And again, if we multiply by 100, that converts it to a percentage. So we know that 0.6 is equal to 60%. 60% of these 45 people chose the guy on the left. So I'm just going to put that proportion 0.6 or 0.60 right there. So that is, again, 60% chose this guy on the left. So if we know that 60% chose him, can we figure out what proportion this is without going back and doing 18 divided by 45? So that's what this next question is about. Why would we use a proportion? Why not just say 27 picked the left and 18 picked the right? So if I told you just 27 people picked the guy on the left, Okay, well, but what if we don't know how many people picked the guy on the right or how many people total? You need two pieces of information to really understand. Okay, 27 here, but how many here? Or is that most of the class? Is that not most of the class? So we have that question. So and if I tell you 27 and 18, well, you can see that this is obviously more, but your brain has to do a little extra work, right, to figure out how much more. So this question is asking, what's the advantage of saying 0.6 or 60% pick the guy on the left versus 27 people can pick the guy on the left? So think about what's that difference there. And really what it comes down to is if I say 60% pick the guy on the left, then I automatically know, well, out of 100%, right, it has to be 100% of people. Can you easily tell me what proportion or percent pick the guy on the right? Well, if it has to add up to 100%, then I know that 40% must have picked the guy on the right. There's only two options. They either choose left or right. If I told you 27 picked the guy on the left, you wouldn't automatically know 18 picked the guy on the right because you would have to know how many people total, right? So if we use a proportion, it's almost like shorthand. It gives us more information with fewer numbers. I could say 60% and your brain is automatically going to say, okay, the other one's 40% versus 27 and 18. You would have to know 45, subtract. It's a lot more brain power involved. So this is why we're going to use proportions, just because it's kind of like shorthand. It gives us two answers for one. Now I want you to think about what are some possible explanations for why we see this pattern where 60% chose the guy on the left and 40% chose the guy on the right. Why do you think we might see that? Or in other words, what are some ways that you think people might be using to decide who to pick? And again, you may want to pause and mull this over. So usually this is like a nice little class discussion, right? So I would ask, how did you pick? How did you pick which guy is Tim? And I often get people who say, I picked the guy who looked most like a Tim. Right? Now, most like a Tim according to who? According to you, right? So that's usually one way that people use is they look at these and they think about what they think a Tim looks like, right? You may think about any Tims that you know and think, well, which one of these looks more like what I expect a Tim to look like? So we are going to call this, basing it based on, well, he looks like his name is Tim. We're going to call this the facial prototype hypothesis, right? So what this is basically means is we're going to test this hypothesis. Do we think that people have facial prototypes? If you hear a name, do you tend to think of certain characteristics of what that person would look like? Or have you ever met somebody and they tell you your name and you're like, you don't look like a Charlotte or whatever the name is, right? So in this case, if these guys both came up to you and introduced themselves as Tim, would you go, he doesn't look as much like a Tim versus the other one? Right? So facial prototype hypothesis is that each of us have this idea, this prototype or this image in our brain of what a certain name looks like, right? If you hear a certain name, do you have a face that kind of matches that in your mind? So, right, some people would say, yeah, I think so. And some people say, no, I don't think so. So that's what we want to test today is, do we think that when I ask people to pick left or right, do we think they're using a facial prototype to make that decision? Oh, this guy looks like Tim, that guy doesn't. Or maybe they both look like Tim, but this one looks more like Tim. Or sometimes when I ask the class too, okay, if you didn't use that method, then how did you pick? And a lot of times the answer to that pretty much is that, well, I just chose. I just chose one. I just picked one. So that second option we're going to refer to as choosing randomly. All right, so these are the two kind of options that we're going to examine, because either, right, these are probably just the two ways that people choose. Either you think one of them looks more like a Tim, or you don't think either of them looks more or less like a Tim, so you just choose one, choose randomly somehow. Okay. So what we want to try to just figure out from today's lesson is, okay, this data, the 27, 18, and 45, this is the real data. And this is before, like I said, I don't give any hints about what I'm expecting. I just say, here are two pictures. How much does the guy on the left look like Tim? How much does the guy on the right look like Tim? Which one is Tim? Right? There's no hints or anything. It's up to everybody to come to their own decision. And this is what the data looked like. 60% said guy on the left, 40% said the guy on the right. So we want to figure out, well, can we sort of figure out from that data whether this facial prototype thing is really a thing? If there's a certain pattern to our data, does that suggest that people are using either one of these methods over the other one? Okay. So we're going to try to decide between these two options. What do we think it is? Facial prototypes, or are people just choosing randomly? And that's how we got this particular pattern. It's just random. Okay. So let's talk a little bit about random variation. We've been talking about that since class 2 or 3 or something like that. So let's revisit this idea of random variation. So let's say inside people's heads, if we were to crack them open and take a look, people are doing something, but there's no real effect of this facial prototype. This is really just it's something that people think is happening, but maybe it's not really, right? Maybe there's no real evidence for it. Maybe people are wrong, right? This is the whole point of doing research and statistics, is try to figure out, do people have a facial prototypes, or are we picking at random? So think about what result would you expect about if there really is no facial prototype? So if everybody is just picking completely at random, then about about what percent would you expect to pick the guy on the left, and about what percent would you expect to pick the guy on the right if everybody chooses at random? So hopefully kind of makes sense that, if everyone's choosing at random, then I would expect about, right, maybe not exact, but about 50% choose the person on the left, and about 50% choose the person on the right. Because there's no reason for anybody to pick more of one or the other, then we would expect people to pick them fairly evenly, right? Now, this next question, would we always expect the result to be exactly like that? If we took 100 people and we gave them this question and we know they're all choosing randomly, are we always going to get exactly 50% left and 50% right? Or is this more like a model that we're using to start with, right? This is a rough model that we expect it to be close to that, but maybe it's not always going to be exactly right on, right? So in this case, this is really a model of random chance, or a model of choosing randomly. So maybe we'll put it that way. This is a model of choosing randomly. If everybody chose at random, we would expect it to be about 50-50. But if it turned out to be 51-49, that wouldn't really blow my mind, right? Okay, so a couple more people happen to choose one over the other, or one more person. If it was 48-52, again, I wouldn't be that surprised because it's pretty close to 50-50. right? So the model says we would expect about 50-50, but it doesn't mean it's always going to be exactly that, right? Probably it's always going to be just pretty close to 50-50 is what we would expect if people are choosing randomly and there is no facial prototype. So hopefully you're following my logic so far. So next we want to create a model of what we think may be going on in the greater population around us. And this is a tricky model, right? You may wonder, okay, so what do we base the model on? Do we base the model on the facial prototype hypothesis? Or do we base the model on the choosing randomly hypothesis? Most people intuitively would say, I'm going to make my model assuming that I'm right and that there is a facial prototype. The problem with that is, okay, so for your model, what percent do you want to use for left and what percent do you want to use for right? And it will depend on who you ask, right? I may ask one person, they say, I'm going to do 75 and 25%. I ask somebody else and they say 60-40. I ask somebody else and it's 80% and 20%, or maybe they think the guy on the right looks more like Tim and so they say 20% and 80%. The problem with trying to build a model off of this hypothesis is we don't know what the data would really look like if that hypothesis is true, right? If people really are using those facial prototypes, well, then what numbers would we expect to get? What proportions would we expect to get? I don't know. And I may say something different than you would say versus one of your other classmates would say. We all might have slightly different opinions, especially if people think the guy on the left or the right looks more like Tim. That's going to influence their decision, right? So it doesn't really make sense for us to start by making the model based on the research hypothesis that we're interested in, the thing we think or we suspect might be going on that we're testing for. So in statistics, since we don't really know what that alternative actually would look like, we start by building our models based on something that we do know what it looks like. We do know about what we would expect if people are choosing randomly. So here it says, we'll create a model based on our beliefs about what we would expect if people were reacting randomly. And again, you can take a look at the guiding notes that I provided. This seems counterintuitive because we want to test the hypothesis the research hypothesis that we think is actually happening, but random is better for making a model. So again, the reason why is because what would a model of facial prototypes look like? We don't know. We don't know what that would look like. What would a model of someone or of people choosing randomly between two options look like? Well, if I said everybody chose at random, we would expect probably about 50-50. Again, about 50-50, right? It's not always going to be exactly, but we know if everyone's choosing randomly and we ask enough people, it should settle somewhere around 50-50, about 50% left and about 50% right. So we start with what we know, what we can figure out without guessing. And without guessing, we can figure out what a model of random looks like. So we start there. And this is going to connect with this idea of p-values that we've talked about. We're going to get more into those p-values. And the likelihood, that word should be familiar, of something happening randomly. This is the basis of why we use this backwards logic in statistics and we rely on p-values where we kind of start out assuming nothing interesting is happening. Because if nothing interesting is happening, we know what that would look like. If it's not interesting, people just choose totally at random, we know about 50% will be left and about 50% right. Now, if there's something else going on, something interesting, like people have facial prototypes, then we would expect it to not be 50-50. But we don't know exactly what we would expect. How much left and how much right? Is it 60%, 70%, 80%, 90%? We don't know. So this is really the logic behind p-values. So with p-values, we start by assuming random chance. And then if the p-value is very low, this means the probability of it happening of our of the result that we see, the probability of the result we actually see when we collect data, if that probability is very low, that means the probability of that result we see happening randomly is low. And if it's not random, then it must be the other thing. It must be the alternative, that there is something happening. So we're going to get more into this null hypothesis, alternative hypothesis. We're going to talk a lot about this. I know we talked a little about it before. We're going to continue to expand on this. And like I've said before, this is a really difficult concept. There are people who have graduate degrees and have completed their thesis, and they probably, if you ask them what p-value means, it's a concept that stumps a lot of people. The p-value is really, what's the probability I would get this result if the null hypothesis is true, if nothing interesting is happening, if people are just choosing at random. So we always start with our random model because at least we know what that would look like. Okay. Now let's all pretend that we're acting randomly to pick Tim. How could we be sure that we're acting randomly? Because as humans, we're actually really, really bad at doing things randomly because our brains are designed to look for patterns and make patterns. That's how the human brain operates. So if you ask someone to do something randomly, it's actually really hard to do that. So what's a way that people often use to choose randomly between two options, right? If you're trying to decide this or that, what is something that people often do to choose and make sure they're doing it randomly and it not being influenced? Well, we could flip a coin, right? Assuming that this is a fair coin. About half the time it's going to land on heads and about half the time it's going to land on tails. And that's sort of what we're expecting if there's no facial prototype. If it's just random, if people are just totally random picking, then we would we would expect about 50% and 50%. Same as if everybody just flipped a coin and we counted them out. Okay. So, again, this data is based on what we've done together as a live class in the past. Again, it's difficult. I would hand out pennies to everybody just so you know the context. Everybody has a penny. And then we say, okay, ready? Everybody flip your penny. And we'll count how many heads and how many tails we got. And we're going to go ahead and say that because we need one of these people to be heads and one of them to be tails, we're going to call the person on the left, this guy on the left, he's going to be heads. So if your coin lands heads, you're choosing him. And the guy on the right is tails. So if your coin lands tails, then you would choose him. Okay. So we did this all together as a class. Again, this particular day in class, there were actually only 40 people available. But this is what happened. This is how it turned out. We got 25 heads out of 40 flips total. So that means we had 25 heads and 15 tails. And this is what actually happened in class, right? Everybody flipped a penny, and I asked, raise your hand if you had heads, and we counted. Raise your hand if you had tails, and we counted. And we made sure that it all added up to 100%. And out of 40, 25 came out heads. So if we convert this to a proportion, the proportion would be, well, let's find out. 25 out of 40, that's 0.625, or 62.5%, right? And for our sake, for this classwork, I'm going to leave it written as a proportion because when we get into, we're going to do a simulation, and the simulation uses the proportions that look like this. If we put in 62.5, it'll yell at us. So we want to make sure that we're using the proportion as we see it, 0.625. And again, to get that proportion, you'd say, okay, take the number of the thing we're interested in out of the total number, gives us the proportion. So 60.625 or 62.5% ended up with a coin on heads, which then I can figure out that that's what, 38.5% had the guy on the right had tails. Okay. So if we're all choosing randomly by flipping coins, this is a potential result that we could get. Now, is that the only result we would get? And this question, is this an empirical sample? Well, in this case, no, it's not an empirical sample. So let's do a little review of some terminology here. So an empirical sample is real data that has been collected. Like the real thing. When I ask you to vote based on the faces, and then I tally up those votes, that is the empirical sample. That's the actual observed result that we see. What we're doing with the coin toss is called a simulated sample or hypothetical sample, right? And I'm usually going to use the term simulated sample. So we like to define the difference between, empirical is real data. Simulated is if we run a simulation to see what it might look like. This is a simulation of what it might look like if people chose randomly between two faces, right? People aren't really choosing based on the faces in that case. They're choosing based on this simulation of randomness. Now, an empirical sample, like I said, is our actual data. So empirical sample is our actual data. This is what really happened when people chose between the two faces. So, and this is because empirical really means observable or based on experience. So if you hear someone talking about empirical research, that means that they collected a sample of data and they looked at what happened. They actually look at what happened in, for reals. And that's the empirical part. It's the, okay, based on my experience, based on what we see, this is what's happening. So an empirical sample is a real sample of real data, not hypothetically what might happen if we, or what we see happening in a simulation, right? So flipping coins, that's not really how we all picked the data, right? That's a simulation. Just like in that second classwork, we're coming back to Martin v. Westvaco, taking it way back, that discrimination case. The real data in that case was the ages of the people who were actually fired. The simulated data was what we did when we put all the ages on pieces of papers and scrambled them up, and then we chose 3 at random, right? That was a simulation. That wasn't really people are being fired. It was a simulation so we could see, like, well, if we did it at random, what might that actually look like, right? So in this case, our empirical sample is the data that we see in question 1. The empirical sample is where people really voted, and we saw that 60% voted for the guy on the left. When, as a class, we flipped pennies and we counted up, we got 62.5% for the left based on our simulation. So again, this shows us that our models, it doesn't always come out exactly like our model predicts, right? In this case, we didn't get 50-50. We got 62.5 versus 38.5. That's, a ways off from 50-50. So that tells me, well, maybe this 60%, even though it's not 50-50, maybe people are really choosing at random, because we could see 60% at random, right? We had even more than that when we just flipped pennies. Now, the same issue as when we did Martin v. Westvico is, well, that's just one simulation. That's just one way that it could come out. Is it always going to turn out that if we flip 40 coins, 25 are heads every single time? No. Just like it's not going to turn out 50-50 every single time. So if we flip 40 coins again, will we always get 25 heads? No. We could get all sorts of things. We might get 24. We might get 26. We might get 19, 18, 20, 21, right? There's a bunch of different options that we might get. And it would be happening at randomly if we're all just flipping a coin. So there are many different results we could get at random by flipping coins. It's even possible, right? So I'm saying possible, not probable. Those are two different things. But is it possible that if we flipped 40 coins, all of them would come up heads? Yeah, it's possible. It would be super, super, super weird, right? We'd be like, oh my gosh, what are the chances of that happening? Not very high. But it is possible that we could get 40 heads or 40 tails. Of course, probably most of the time it's going to be closer to 20 and 20. It's going to be closer to that 50-50. But again, if you just look at one time, that's not a very good measure. We want to look at lots and lots and lots of times what happens. So if out of all the times that we would flip 40 coins, how likely are we to get, 60% versus 40%? And that's really the logic behind the statistics that we're doing. So random can look lots of different ways. So we don't want to look at just one case of random. We want to look at, okay, if we did this randomly tons and tons and tons and tons of times, then how likely is it that we would see a result like our real result? If it's pretty likely, if it comes out 60% a lot of the time, and that's not so weird, then we could say, well, then this could have happened randomly. If it turns out that if we do this lots and lots and lots of times and we count, okay, how many times did we get 60% or more extreme, and that number is very, very low, it's really weird, it's very unlikely to happen when we're flipping coins, then that would be good evidence for us that this data, not randomly picking, that there is some evidence for something going on, and that something being the facial prototype hypothesis. So we use that p-value to really help us kind of decide, okay, based on all this simulated data, based on our model of random chance, how weird would this result be? If it's not very weird, then we just assume, yep, could be random. If it's super weird, if it turns out this is like barely ever happens, then we'd say, I don't think it's random. I think it's the other thing, right? I think it's that facial prototypes thing. So, you can probably hear my dogs in the background. So it seems like a whole lot of trouble to stimulate random samples again and again and again. We could sit in class all day and flip our 40 coins and count, and flip our 40 coins and count, and flip our 40 coins and count, and flip our 40 coins and count. And even then, that's only like 5 times. We want to see, like, if we did this 1,000 times, what would it look like? If we did this 10,000 times, what would that look like? We want to look at some big numbers. We want to see, if I did this loads and loads and loads of times, what might that look like? So, since nobody's got time to sit around flipping coins all day, we ingenious humans have invented some shortcuts, some nice little handy websites and stuff to help us do this stuff, where we could tell the computer, hey computer, flip 40 coins 10,000 times, and the computer can go, all right, and it does it. It does it way faster than we ever could, and probably with fewer mistakes counting. So that's what we're going to do. We're going to say, hey computer, do all this work for me so I can see what the result looks like, so I don't have to do the work myself. So we're going to use this website, tinyurl.com/coin simulations. Let me pull that up. tinyurl.com/coin simulations, and it's going to redirect us to this website. So you notice this looks kind of like what we've got. Let's see if I can make this a little easier for us to see both at the same time. So this picture that you see here is just a screenshot that I took from this website. So we're starting out with the website blank, right? We haven't run any simulations yet. But this website lets us run a simulation where we're flipping coins. Now, let's start by just doing one simulation. So here, we're going to run the simulation, and then what I'd like you to do is to label, what do all these different parts mean? Because then I'm going to have you run several simulations on your own, and you need to be able to understand what are the different parts, and how are we interpreting them, right? So I want this simulation to basically represent, okay, if I ask 45 people, because that's how many we really had in our empirical sample, if I asked 45 people to flip a coin, I think my mouse is dying. There we go. So here we have probability of heads. So this is just asking, is it a fair coin or not? Yeah. We're going to leave it as a fair coin, 50% chance that it's head, 50% chance it's tails, because that's pretty much, that's what it is, right? Now, how many tosses, how many coins are being tossed? We want it to match up with our simulation so we can then compare directly, right? So if we're doing it based on our empirical data, that would be like flipping 45 coins. So the number of tosses is the number of people voting. Okay. Then the number of repetitions, we're going to start with just one, so we can see one in action. Okay. Now down here under choose statistic, we'll talk a little more about this in a moment, and then we'll label all of our stuff. Okay. And you could hide the coins, you can have it animate, or just do it all at once. For this first one, I'm going to have it animate so we can actually see the process. After that, even if you leave animate on when we do big numbers, you'll see it just, the computer's so fast, your eyes don't even see it. So here we're saying, okay, I have a fair coin. I'm going to toss it 45 times. I'm doing this only one time right now. Do it. And so the computer is now flipping 45 coins and it's counting. You can see it's up top. This is all of the coins it's flipping in its little computer brain. And then it's counting, okay, this is how many are heads. You can see the shinier color. And this is how many are tails, or the darker color. So, would you look at that? That's kind of amazing. Never actually had this happen before. See, but randomness. You never know what you're going to get. So the computer flipped these 45 coins and it counted, okay, that one's heads, that one's tails, that one's heads, heads, tails, heads, tails, heads, 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 tails, tails, heads, 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 and so on. And so it just flipped all 45 and then it said, okay, let's count up how many were heads. 27 came out heads, which is funny because that matches our empirical sample in this case. And if you're doing this at home, you probably got something different because it's random. And 18 tails. So that's really interesting. So let's go ahead and go back to our classwork and just label this. So this top row where we see the 45 and then we see the number of coins here, right? So in my screenshot, you can see the numbers are different. They're 23 and 22 because every time you do it, it's probably going to be a little bit different. So in this case, since 45 people voted, we toss 45 coins. We see results above, right? We see all the 45 coins. This is the 45 coins. Now, what does this set right here represent? Well, this is number of heads. And again, that's out of those 45 coins that were tossed. Down below, the darker color, this is the number of tails. Again, out of 45. So instead of having everybody flip their coins at home and trying to coordinate and then try to do it 1,000 times or 10,000 times, we're going to use the computer to do it really quickly for us. So what you probably may or may not have noticed is when I ran this simulation, it added a little dot right down here. And I'm going to choose statistic. I'm going to switch it so it says proportion of heads, right? We want it to match what we see in our classwork here. Proportion of heads. And again, why do we use proportions when we have two options? Well, because it's like shorthand. We get 2 for 1. So, okay, I did one flip. I want to know, we could see that it dropped it down. It calculated it automatically that the proportion was 0.6, and you see it's proportion of heads. So out of these 45 flips, 60% ended up on heads. That's the proportion, just like we saw in our very first question. If we were to do it again, right, I'm not going to reset it. I'm just going to do it again. Okay, then this means I'm flipping 45 coins again. And let's see what happens. Oh my goodness, it's coming out exactly the same. This is what I love about random stuff. It surprises you. Random stuff doesn't look random a lot of the time. And this is because our little human brains are trying to make patterns. So flipped 45 again, and it miraculously came out 27 heads and 18 tails. And so what it did is it calculated, well, that's still 60%, hasn't changed anything. So it dropped another little dot on our dot plot. And so we see we've done 2, and both of them have come out with proportion of heads 60%. I'm going to do one more just because I really don't think it's going to come out 27 and 18 again. Okay, this time it came out really extreme this time. Interesting. So it's still counting. And if we turn off the animate, it'll just flip them all at once and we don't have to watch and wait for it to do all the counting. But this time it looks like we're going to get 30 heads and 15 tails. And again, if we just flip coins at randomly, this could totally happen. That's what's happening. So this time when it calculated, it said, okay, we got 30 heads out of 45. That's 0.66667, or if you round, 0.67. So down here on our dot plot, you see there's a little dot that got added at 0.67. So what it's doing is each time we're running a sample, we're running a simulation, it's flipping the coins, it's counting up how many heads, how many tails, calculating what's the proportion of heads, and then it adds a little dot to our dot plot. And so if we could do this, I'm going to turn off animate so you can see how fast it works. And then if I draw a sample again, boom. This time it was 24 and 21, and it added a little dot. It calculated the proportion is about 0.53. So if we keep doing this, draw sample, draw sample, draw sample, draw sample, draw sample, draw sample, it's going to keep doing it, right? And thank goodness for computers and how fast their little computer brains work. Well, thank goodness for humans who invented computers. We can see it starts to form a distribution on our dot plot down here, right? So we can start to see, well, it looks like we've gone as low as 40% heads, as high as 67% heads, and we got a bunch of stuff in between. And so what we suspect should eventually happen is it should settle somewhere around 50%, right? If it's really a fair coin and it's really random. But if you just do it once or twice or 3 or 10 times, then it's usually not going to work out to 50%, right? So we need to do this a bunch of times to see if we did this 1,000, 10,000 times, what is that going to look like? Okay, so I'm just going to add a couple notes here. So I don't know if I can do a little arrow here. So we put our proportion from our real empirical sample, the proportion that we're interested in, that we want to compare. So in our case, since our actual empirical data from question number 1 was 60% heads, we want to say, okay, if I do a bunch of simulations, how likely is it that I get 60% at least heads? Okay. So we want to select for proportion of heads, and then what we're going to do is we're going to plug in the proportion we're interested in this little box that says as extreme as. So we're going to put that in here, and again you want to make sure it says proportion of heads is selected, not number of heads. And then down below, I can't do a down below arrow, but down below, let me just put below, it calculates proportion of heads and plots it on our dot plot. Okay, in this case, it was only done once, so there's just one dot. Here, I've done it, and you can see I've done it. I just started clicking that button a bunch of times. I've done it 22 times. If I do it again, I'll say 23. And so each time, it's just counting. So out of 23 times, we can see we should count if these should be 23 dots here, because there's a dot for each time we do it. So what I want to do is I'm going to put in my 0.60, since that's what we really got in our empirical sample. And I want to know, like, how often does that happen? So I put in my proportion and click count. And so what it does is it figures out, okay, where is that? And it's saying that 4 out of those 23 times, we had a proportion of at least 60% or higher of heads. That means that the rest of the time we have fewer than that, right? It was less than 60% heads. So this will calculate for us, it'll automatically count up all of our flips, all of our simulations that we've done, and it will find out how many of our simulations look like our empirical data. And then from there, we can figure out if a bunch of them look like it, then it totally could have happened at random. If it's super, super rare, then probably it's not random, and we would reject that null hypothesis. Okay. So I'm going to go ahead and reset this, just because I went a little crazy and just started showing you stuff. So I'm going to reset. If you press that button, you're going to want to reset in between. You'll see I'm going to have you do several different simulations where you have different numbers of tosses and different proportions that you're going to put in. Right now I'm leaving this the same, okay, because we're still working on the first one. So let's do it for 10,000 simulated samples and see what would that look like. Okay. And I know I say fill in the graph above. Again, this is uh, in the olden times when we used to actually draw on paper. I know some of you print out your classwork and draw on your paper, so you can still do that. If you're doing it like I'm doing it and you're doing it on the computer, it's okay if you skip this part, right? Or maybe keep a little notebook where you do this. So let's do it for 10,000 simulated samples. So let me show you how to do that. We're always going to leave this probability at 50%. We're still doing 45 tosses because we're still talking about that original class. But now, instead of doing it just one at a time, I'm going to put in 10,000. I want the computer to flip 45 coins, 45 fair coins, 10,000 times for me. And again, think of how long that would take us. And then we're going to, okay, ready computer? You're going to do it 10,000 times? Draw samples. And it did it. That's how fast it works. So that's why we use computers to do simulations a lot of the time, because it just goes so much faster. So we did 10,000 simulated samples because, again, this isn't people really voting. This is what it might look like if people were flipping a coin to choose to vote, if they were choosing it randomly. And we can see in this case, when we did it 10,000 times, out of those 10,000 repetitions, 1,195 were like our sample or more extreme. So that means about 12% of the time, right, if we figure out that proportion, that probability, how many times it happened out of how many times total, is about 12%. So about 12% of the time, if we were to flip coins at 45 coins at randomly, we would expect to see a result like our real result. Okay, so in this case, we're saying 12%. So let's go ahead and answer our questions on our classwork down here. So how many simulations did the computer carry out? So we carried out 10,000 simulations, the computer did, right? And you can find that number either from the total right here, or here where it has it in red, proportion of repetitions, the divided by the number, the second number. That's where we can see how many simulations it's counting from. So we carried out 10,000 simulations, and then how many of those had a proportion larger, like at least as big or larger than our sample of choosing Tim? Well, you could see it put the line in and it cut them off here. Ooh, I did not mean to do that. Luckily, all I have to do is go back here and put that back where it's supposed to be. So note to you, don't go pulling and dragging this because it's going to change stuff. So how many of those are after this cutoff point? And you see how if we have a bunch of dots on a dot plot, it eventually turns into a histogram, right? Because we're just squishing all those dots into stacks. So here we can see the number that were at least like our sample is 1,195, and that's what I got, right? I got 1,195 proportion at least as large as our empirical sample, as our real sample. Your number, if you're following along and doing this with me, it is really unlikely that you got exactly 1195. You probably got something a little bit different because, again, it's random. So in this case, I could interpret that as about 12% were like our empirical sample or more extreme, right? It's at least like our sample. They could be even more extreme than that, and that's okay. So this is how we're going to figure out how likely something is to happen. And then based on how likely it is when we're doing it at random, we can figure out, well, is that likelihood like acceptable? Is that where it totally could be random? Or is it super weird? Is 12% super weird? We haven't crossed our super weird threshold we talked about before yet. So at 12%, I might say, well, it could be random. It's low, but it's not that low, right? It's more than 1 out of 10 times. So it could be random based on this, right? That result that we're getting, this is sort of representing our p-value. So just to review, what does each simulation represent? And then what does the sampling distribution represent? What we're looking at right here, this is a sampling distribution because we did a sample, we calculated some value, we calculated the proportion, and then you plot it. Do another sample, calculate your value, and plot it. Do a sample, calculate your value, and plot it. Do it over and over and over and over and over and over 10,000 times. And our result is a sampling distribution. And again, it's called a sampling distribution because it's a distribution of what it looks like if we take a bunch of samples, right? In this case, simulated samples. So each simulation represents if 45 people were voting randomly by flipping coins. That's what we're simulating, right? We're simulating, okay, if you were to flip your coins and use that to tell you if it's heads, the guy on the left, if it's tails, the guy on the right, that's what we're doing. And we did it 10,000 times in the computer. So we do this over and over and over until we get a distribution of what we're calculating. This is our sampling distribution. The histogram that shows all the results from all of our samples is the sampling distribution. Because again, a distribution, histogram is just a distribution. How did our results, how are they distributed? And then in this case, this represents if we did 10,000 samples, simulated samples. So the sampling distribution, what we're really going to be using it for, represents all the possible outcomes we might expect if we were doing, I wish I had better words for this, but if we're doing something randomly, right? In this case, if we were randomly picking between the two heads or between the two faces by flipping coins, well, if we did it 10,000 times, here are all the different results that we got across those 10,000 times. So the sampling distribution represents all those possible outcomes that we might see. You can see there's some dots way down here and there's some dots way up here. It's possible when you do something at random that you could get a really, really extreme result, but it's super rare because there's hardly any down here. There's hardly any up here. Most of our results are around the 50-50 mark, right? If we look 40.47, 0.53, 50% is right here in the middle. So most of them stack up close to the 50-50, but of course they're not all exactly 50-50. We have some that came out lower, some that came out higher, but the ones that came out really, really, really low, that's rare. The ones that came out really, 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 really high, that's also rare. So in this case, if we had an empirical result that was way out here at like 73%, I'd say, whoa, that is weird, because we expect it, if they're doing randomly, we'd expect it to be more towards the middle. But it came out way out here, so that's weird. And this is sort of the basis we're going to be using from here on out when we're talking about p-values and trying to figure out, if we're testing hypotheses, is it this or is it that? Okay. So again, and just as a side note, so sampling distribution, this is going to be on the final, FYI. There's always stuff about sampling distribution on final, so start trying to get it. Equals, we take lots and lots of samples, and usually we're talking simulated or hypothetical samples, right? These aren't real samples. We take lots and lots of samples, calculate a statistic for each one. Usually in our class, we're going to be doing the mean. We're going to talk a lot about the sampling distribution of the mean. This example, it's not the mean that we're calculating proportion. So this would be a sampling distribution of proportions. But I think starting next time or the time after that, we're really mostly going to be looking at the mean, because that mean is so helpful because it balances errors. So we take lots and lots of samples, we calculate a statistic for each one of our samples, and plot the result. When we have all the results plotted, that is our sampling distribution. It's the result of all the samples that we got if we were to look at them visually. Okay. Again, this is a really hard concept. If you are struggling to follow along at this point, that's okay. It's very understandable. We are going to keep talking about these concepts over and over until hopefully eventually it kind of clicks. And the great thing about being online, even though we can't do all this stuff together in class, the advantage is it's recorded. So you can always go back and watch it again. And maybe the next time you understand it a little better. And then the next time we do it a little better, right? So keep in mind, you can always revisit this stuff. And I encourage that. Now, for the rest of this, this is going to be kind of like a lab portion where typically we'd all be sitting together in a room on computers, but instead we're all sitting at our homes on computers. And I'm going to have you kind of think through and work through these problems. So, for example, thinking back to the class's opinion of which guy was named Tim, right? Thinking back way to this first one. How likely were we to get that proportion or greater by chance alone? So, in this case, according to our simulation, and again, yours is going to be a little different than mine probably, but according to this simulation, we are about 12% likely, right? Because about 12% of the time it came out like ours. So we're about 12% likely to get a proportion like our empirical sample. I'm going to say get a proportion or greater, like our empirical sample. So think about, okay, 12%, how likely do you think that is? Is that pretty likely? What is your evaluation of those odds? For me, I'm going to say it's a low probability, right? 12% is a low probability, but not super low. Not low enough that I would reject the null, which is the random hypothesis, right? So we talked before about in statistics and like broadly, we generally use about 5% to be that cutoff point. Is 12% below our 5% cutoff point? No, 12% is higher than that. So it's not low enough that I would say that's too weird. Reject the null. At this point, it's kind of weird, but it's not that weird. It totally could happen, right? So in this case, the evaluation of the odds, I would say it could be random, right? This is not strong evidence for the facial prototypes. I would need it to be much lower for me to be convinced that those facial prototypes are at work. This looks like, yeah, it could happen at random. Okay. Now, if the probability of our class result turns out to be really, really, really small, right? If instead of 12%, this was 2%, then does that mean it's likely to have happened by chance or unlikely to have happened by chance? So keep in mind what we're seeing here. This is telling us this is how likely it is to happen by chance. So if the probability is very low, and I would say less than 5% is usually the cutoff that we use, this would mean that it is very, I'm going to leave off the very, that it is unlikely to have happened by chance, right? This p-value, that's totally what we're looking at, represents how likely our result is to have happened by chance, right? And you may remember before I talked about print, P equals, change this, using that print acronym to help you. So I made it up myself, so I have to think about it. So P is the probability, and let me capitalize that P, of our result if the null hypothesis is true. All right, so the probability of our result if null true. And that's where that print comes from. Probability result, probability result if null true. All right, so a little acronym to help you remember. The P represents if the null is true. So if that P value, that probability is very, 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 very low, that means it's the probability that the null is true is very, 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 very small. It's probably not the null. It's probably reject it, the alternative. Okay. So in this case, we got 12%. 12% is above our cutoff point of 5%, so we can't reject the null hypothesis, which means we conclude it could be happening at random. This means this is not good enough evidence to conclude facial prototypes. We cannot, based on this particular result, we can't conclude that facial prototypes are a real thing because we could have had this result just at random, and it's not that weird. Again, why are we using coin tosses? Just as a kind of little revision to represent choosing between two options at random, right? We wanted to make sure we're choosing fairly. We're not being influenced by invisible stuff in our brains. And a way to do that is toss a coin. If it's heads, choose a guy on the left. If it's tails, choose a guy on the right. That's why we're using this coin toss simulation. That's what we're simulating. Now, for the next part, so this, I'm going to have you keep working on this. Let me just show you a little bit more so you're not lost. So next up, let's say, okay, here's data from a different class. It's a smaller class. There are only 24 people in it. So let's see. This is where we're going to do a reset. We want to reset here. So if we have a sample of data from a sort of medium-sized class with 24 people and 15 people choose the guy on the left as Tim, then what proportion is that? Well, again, we want to say, okay, if 15 chose the guy on the left, divided by 24 people total is going to give us our proportion. So 15 divided by 24 is 0.625, about 62.5%. So is this very different from our bigger sample that we started with? So let's call this the medium sample equals 62.5, just because I think that percentages are easier to understand. I know it's exactly the same thing, but for some reason it's just easier to understand out of 100. So the medium sample, 62.5%, chose guy on left as Tim. And in our large sample that we started with, 60% chose a guy on the left as Tim. So are these two samples very, very different? 60% versus 62.5%? No, these samples are not very different, right? That's pretty close. If you consider it could go anywhere from 0% to 100%, the difference between 60 and 62.5 is not very big. So the result is pretty similar. Some of these questions are going to be pretty tough. 18 is one of them. And so if you don't get it at 18, don't get stuck. Just skip over it and keep going. But I want you to think about which one of these two results seems less likely to happen. That 62.5% of 24 people would choose that way, or that 60% out of 45 people. Do you think that they're equally likely to happen? Or do you think one of them is more likely to happen than the other? And again, you might at this point have, like, I don't know. I have no idea. That's okay. Just write your notes to yourself. And then hopefully by the end of this assignment, things will start to click a little more as you get more experience and you see it in action. Okay. So make your notes there. If you've got an idea, absolutely put it down. Might be something you want to talk about in the discussion board too. Now, let me just show you really fast so that you can figure out the rest of this. So we want to go back to our coin simulation page, and again, make sure you reset it. And we want to create a sampling distribution to help us figure out what kind of this sounds really complicated, huh? What kind of sampling distribution, how many tosses and what number of proportion of heads will help us figure out how often a proportion like this or greater would happen by chance. I know that's super wordy. So basically this is saying we did a simulation like the big class. Now we want to do a simulation like this medium class. So we're going to keep a fair coin, but instead of 45, we don't have 45 people voting in this class. How many people do we have voting? 24. So we're going to put 24 in that box this time. So we flip 24 coins instead of 45. I'm still going to leave it, since the next one says run 10,000 simulations, I'm going to leave it as 10,000. And here we're going to have to update this proportion because this 0.6 belonged to the big class. So what do we want to put in here instead? This 62.5%. So the 0.625 is going to match this next class that we're simulating. Right? So you want to put those values in here just to keep track. And then we're going to run 10,000 simulations. So once you have it set with 24, 10,000, and 0.625, you go ahead and do draw samples. And it just did 10,000 flips, or 10,000 times 24. And we see the resulting sampling distribution. Okay? So now what I want you to do is, again, similar to what we just did before, how many of these simulations had at least 15 heads? Well, you'll see that here. It counted them all up, and for me, it's 1559. For you, it's probably a little different. But so you want to record the number of simulations that ended up like ours or more extreme out of 10,000 and use that to figure out the probability. The probability is going to be that value all the way on the right. It's that basically the percentage of the time that it looks like ours or even more extreme, right? Looking into the tail of this distribution. So go ahead and look at yours and make sure you document what you got. And then 21 is another thinker. Give it a good think. 22, you're going to reset again. And this time you're going to do it out of 10 people flipping. So that 24 is going to be changed to 10. And there were 6 people choosing. And so this is going to go back to our 0.6, right, for the next round. And you're going to want to make sure that you update the numbers, put them in what you did here. Again, we're going to want to see 10 tosses. And spoiler alert, this works out to 60%, 6 out of 10 is 0.6. So again, I have you kind of compare, how is that compared to the other 2 classes we talked about? So think about that, jot your notes down, make sure you reset and update your page and then run it again and see what that sampling distribution ends up looking like, right? And then figure out what probability is associated with that. And then finally, we'll have one last class with 100 people. 61 chose the guy on the left. I want you to calculate what proportion is that. How does that compare to the other classes we talked about? Run the simulations by putting in 100 coin tosses and the correct probability or the correct proportion that goes with that. And then look at the results and figure out what the probability is. And this very last question, 27, I want you to look at all 4 of those classes. Look at the original proportion of people that chose the guy on the left. And then look at the resulting probabilities of that happening if we did it 10,000 times at random. The very first one we found was about 12%. I don't want to go all the way back up there. This one, for me, I got around 15, 16%. So let's see, I want you to see what does it work out for you, and what does it work out for a class of 10 and for a class of 100. And then I want you to compare those probabilities. And why do you think, like, another spoiler, they're going to be different. Why do you think that's the case? And so this would be a great one to talk through on discussion board. Like, try to make sense of why is this happening? And then we'll go more over why it happens in a follow-up. Okay. So hopefully that was helpful in demonstrating this simulation website, explaining how to use it, and that gives you enough to work through the rest of this classwork, filling it out on your own. So, and again, remember the resources we've got. Discussion board is perfect. If you get stuck, if you're like, I don't know what to put for this one, I really encourage you, ask each other. And I'll check in, and if I see nobody's responding to your question, I'll chime in and I'll let you know. But I like to let you guys try to figure it out first, right? I don't like to jump in with the answers right away. So you'll notice I kind of keep quiet till towards the end of the time. Because you guys can usually figure it out on your own. You guys are so smart. Collectively, there's so much knowledge. If one person gets it and then they explain it, it's the knowledge spreads. So I think you learn better that way than me just telling you the answer right out. So that's why I like to let you struggle a little bit. We're letting your brains grow and working on building those synapses in your brains and making you stronger. So Thanks for sticking with me. I know this was a long one, but hopefully you have a little fun running the simulation and filling out the rest of this.